right, I'm going to run through these notes a little bit fast, but then take some more time when I get to the example problems at the end. So temperature is going to be a measure of a material's average kinetic energy. So if I imagine a cup of hot water, I imagine the water molecules in there bouncing around faster and hitting the walls of the cup harder and colliding into each other harder. But if the molecules are moving faster, here's a little animation that would give each of them more kinetic energy. This blue circle would represent an oxygen atom, and these little just imagine red that the molecules are hydrogen atoms, and they are bound together then into a molecule. And here we have several molecules. And this is an animation for a microwave. And microwaves are a low energy form of light, too low energy for us to see. So I'll push the little button that says turn the microwave on. And the microwave adds energy into the water molecules and makes them move around faster. And the faster they go, the hotter your water is. And we said earlier average kinetic energy, because if you look at these bouncing around, you can see that some are moving faster and some are moving slower, and it's always changing which one is moving faster and slower. So we just take the average. All right, one handy thing to note is our sense of temperature is not reliable. A good example of that is if you roll out of bed in the morning and you put your feet on a stone floor, like stone tiles, it feels really, really cold. But if you roll out of bed in the morning and put your feet onto a rug or a carpet, it won't feel near as cold, even though both the stone tiles and the carpet are at room temperature. Why they feel different is because the stone tile would be a good conductor of heat. It would allow the warmth of your foot to escape faster into the tile. Another example would just be the outdoor temperature. On a hot, muggy day, I might go outside and think that it feels like 100 degrees outside. But it might only be 90, just with high humidity. That makes it feel hotter to me. All right, there's 3 temperature scales that we should note: Fahrenheit, Celsius, and Kelvin. Fahrenheit is used in the United States and a few other countries. Celsius is widely used, and it's also easy to convert to Kelvin. So most of the world would use Celsius when they're talking about temperature. And Kelvin is best for finding a material's average kinetic energy, as well as some other stuff. And this is our SI unit. So just for some scale, let's talk about some basic temperatures in Fahrenheit. The boiling temperature of water at standard atmospheric pressure is 212 degrees Fahrenheit, and water freezes at 32 degrees Fahrenheit. And at the absolute coldest temperature anything could ever have, we call it absolute zero, and that's when all the molecules would stop moving. That's this temperature, negative 459.67. Our book isn't going to be so precise, so I might even just right now just round this to negative 460. All right, then if we go to Celsius, water boils at 100 degrees Celsius. Water freezes at 0 degrees Celsius. And the coldest possible temperature, absolute zero, is negative 273.15. And I think our book and homework would really just need 273. We don't need it to be 5 significant figures. So I would argue that these look a lot easier to remember than these. Right. And then our last one, Kelvin. First of all, notice I didn't put a degree in front of the Kelvin like I did for Celsius and Fahrenheit. That's just because we don't say degrees Kelvin. So water boils at 373.15, but we'll just say 373. Water freezes at 273.15. We'll just say 273. And the coldest possible temperature, absolute zero, is at 0 Kelvin. That's how Kelvin is defined. Kelvin was designed to have zero at absolute zero, and then the temperature steps from 1 Kelvin, 2 Kelvin, 3 Kelvin, those degree steps are the same as these. So that's why there's a 100-degree difference in here, just like in here. So I would say Those are the most important ones to me. They also seem like the easiest ones to remember. Most of the world would only ever have to worry about converting between Kelvin and degrees Celsius. But here in the United States, we have to also worry about converting to and from Fahrenheit as well. So if you have a temperature in Fahrenheit, you can use this equation and find what that temperature is in degrees Celsius. And then you could take that degree Celsius and plug it in here, plug in a certain temperature here, and you would get it in Kelvin. And this is another thing that is usually handy to remember when you're in a science class. All right, the temperature in Kelvin is always going to be 273 more than whatever it is in Celsius. All right, section 2, definition of heat. Heat is going to be the flow of energy due to a temperature difference. So you shouldn't really be saying like your body has heat. You don't have heat. Heat is the transfer. So heat is describing energy that's coming or going. And so its SI unit is also going to be the joule, just like all of our energies. Some other units that could describe heat or energies are the calorie, the capital C version of calorie, and the BTU, the British thermal unit. So I'd already told you that what 1 joule stands for, it would be the amount of work done by a 1 Newton force over 1 meter, because 1 joule is equal to 1 Newton meter. But you could also rewrite that as a kilogram meter squared per second squared. So that's what a joule represents, how much energy it represents. But just for fun, let me tell you what these stand for. 1 calorie is defined as the amount of heat, energy moving into the object, that it would need to raise the temperature of 1 gram of water, which is a very small amount of water, by 1 degree Celsius, which would also be 1 Kelvin. So this is useful and pretty standard. Then we have capital C calories. So I labeled these as quote-unquote US food calories, because if you look at your cereal box or something, it'll tell you how many calories it has per serving, like 200 calories. But that is with a capital C. 1 calorie with a capital C, that could heat 1 kilogram of water, which is a liter of water, by 1 degree Celsius. So you notice that here it was 1 gram, now it's 1 kilogram. So this calorie is 1,000 times bigger than that one. So there's that conversion right there written out for you. So pretty much what the rest of the world does is just calls them kilocalories, or kcals for short, instead of actually just having to keep track of capital C and lowercase c. I vote we just switch. And while we're switching, let's just also say that all prices have to include tax and be done with it. While I'm getting frustrated at units, let me introduce the British thermal unit. It is the amount of heat that you would need to heat or raise the temperature of 1 pound of water by 1 degree Fahrenheit. So if I could pick maybe 2 of these to maybe say that we should agree to use, it would be the joule and the calorie. And I wouldn't mind just kind of getting rid of these. If you ever needed to convert between them, 1,000 calories is equal to 1 food calorie. 1 calorie would also be equal to 4.184 joules, and 1 British thermal unit is equal to 1,055 joules. In your book, they ended the section with an interesting bit about how most materials will expand as they heat up. It's just kind of like a hot air balloon. You heat up the air, and so then it would expand. So now you have the same amount of mass, but it takes up more volume, so it's less dense, so then your hot air balloon will rise. But one major exception to that, it's not the only exception, is water near freezing. So I have a graph here for volume and temperature. So what I could do is maybe imagine some ice, and we heat it up, and it would expand. Because as we went more and as we warmed it up, it took up more volume. As we warmed it up, it took up more volume. So that's fine, that's normal. But then this is the weird part. When it changes from ice to water, it shrinks again. Or it shrinks, it contracts, it gets smaller. So that's the weird part right there. And I'll write in there, this is where it melts. This is when it was ice. And over here is when it's water. And it also shrinks a little bit more, even though it's all melted to water now, up until about 4 degrees. The volume of the water is still contracting until you get to 4 degrees. And then it will start to expand again as it warms up. Right? The general rule would hold there. Have you ever had a water bottle in your car that was pretty full and you left it in your trunk in the winter? It was water, but when it freezes, the molecules all have to rearrange and it has to expand. And so the water in there expands and it'll probably just crack the water bottle. And then hopefully you find it before it melts again all over your trunk.